Right. Okay, so I'll start. So my name is Stephen, and I'm a researcher at the University of Edinburgh. And today I would like to share with you our recent work on the remote TCP connection offloading. This is work done by myself and our PhD student Shuo, who was here earlier today, and Tianyi, and also Michio, who is the leader of the operating system and network group. So we are in a networking conference. We all know what this is. But at the risk of boring you, I'm going to go through the scenario again. So this is a typical deployment setup of a cluster, where in this case, we have 3 machines here, of which individually they are connected via a 25 gigabit Ethernet to a switch. And to the outside world, there is a higher bandwidth link, which is 100 gig. Let's say we have a front-end, one of the machine is acting as a front-end server, let's say the red one in the middle. So this server receives client requests from the outside world, for example, HTTP GET, and depending on the payload, the application payload, like the hook data here, it performs some processing or proxy and so on. So for example, in this case, it decided that it should be forwarded to an application server on the left-hand side, right? So this is forwarded to the server on the left, which is a backend server, which performs some processing, does a reply to the front end. And finally, the front end reply to the client after some encapsulation or encryption and so on. So there are some problems here. So the first one, very clearly, the link to the outside world is 100 gig, whereas the connection to the front end server is only 25. So even though the internal connection can talk to a different backend server simultaneously, it can only reply to the client at 25 gigabit per second, which means the other 75 is left idle. So then we can simply run more front-end servers or collocate them across the cluster, right? Well, it's not that simple. So I'll demonstrate this using another example. So this one is a more concrete case. Let's say an object store. So again, we have a front-end server denoted by the red, and also some back-end servers that store actual data. When a request comes into the object gateway, it passes the request and look up the object. And it turns out the object is on the left-hand side. So it issues a request to the object storage server on the left-hand side, which retrieves the data from the disk. After that, it replies the data to the gateway, and finally the gateway encapsulates it in the HTTP payload and replies to the client. So we performed a measurement on using Ceph and Rados gateway of this setup using a 25 gigabit link and 100 gigabit links, backend links. So on the column on the left-hand side shows the 25 case. And on the top figure, we have the throughput. So it is very clear that the bandwidth is kept physically at 25, despite that the outside world has 100. And at the same time, we see the CPU load of one particular server, which is the front end, is significantly higher than the rest. This is because the front end server is doing a lot more processing than the back end is doing. So even if the back-end servers are connected by 100 gig links, it does not improve it that much. So obviously, we get a much higher throughput than the 25 case because it is not a physical bottleneck anymore. But the issue of the CPU usage still maintains. So this is the typical layer 7 load balancer case, which we have just seen, which is request-oriented and is application level. And there are other options to solve this, right? So one of them is splicing, which is also connection-oriented, but it cannot touch the payload, and it may require some smart NIC or other hardware support. And then there are options such as content-aware routing, but they have their own limitations. For example, they cannot support encryption, require hardware, and have limited request and response sizes. And finally, existing work includes connection migration, which are request-oriented and have been shown to provide line rate performance. But again, they require programmable switch support. So to this end, we introduce our solution, which is called XO, which means crossover. And we follow 3 specific requirements and approaches. So the first is we want to eliminate the need for special hardware support. For example, we don't need the programmable switch or smart NICs anymore in order to support the system. Secondly, it must be transparent to the client, which means that the client must be able to operate as if it is using a L7 proxy. So in order to support this, we need to use different packet filtering methods, such as eBPF and TC-flower and so on, which I will explain in a moment. And finally, we would like all the backends to be able to perform direct server response in order to fully unleash the potential of the 100 gigabit per second link. So the method we're using is called, we call it TCP connection state offload. Offload in the sense that we're offloading the processing to another place by moving the TCP connection endpoint from the front end to the back end directly. So in order to perform this, there are several challenges. So the first one is that it requires many non-atomic operations to serialize a TCP connection. So the Linux kernel already provides an option on this called the TCP repair. However, on its own we cannot use it on its own. We need to do a lot of get sort of operation to get information such as queue length, sequence number, and so on. If we are using TOS, we have to also serialize the TOS state. And because we want to eliminate the need for a programmable switch, it means that packets, the flow must be forwarded and packets must be manipulated in order to act as if nothing was happening in the backend. So in order to do this, we need to perform packet filtering using methods such as eBPF classifiers, netlink filters, TC-flowers, and so on. And finally, to move the endpoint from one place to the other and set up all these rules may require many RPCs. So the second challenge is about using the TCP repair mode. Because when a socket enters TCP repair mode to the kernel, it looks like it basically disappeared. Right? But the client does not know that. So if the client issues any retransmission or acknowledgement packets, the kernel simply replies with a TCP reset because it doesn't exist. So in order to solve all these challenges, we designed a offload protocol and pack all this into one place. So I'll illustrate this with a scenario. So we have a client machine here and then two server machines, server A and B. So let's say the client opened a TCP connection, performed a TLS handshake, and then sent an HTTP request to server A. So server A received this request and decided to offload this connection to server B rather than processing it on its own. So it first blocked incoming traffic in order to avoid any retransmitted packet from the client, triggering the reset. After that, it serializes the TCP socket and also any associated TCP TLS states. After that, it issues a request to server B saying that I want to offload this connection to you. So server B receives this request, passes it, and it also blocks incoming traffic on this flow in order to protect the integrity of a restored socket. So after that, it proceeds to do the opposite. It deserializes the TCP connection, restores any TLS state, and it installs a source IP modification rule for this flow in order to make it look like it is coming from the original server, server A. And then it unblocks, because the socket is now ready, it unblocks incoming traffic. And then it tells server A that my socket is ready, you are now ready, you're now okay to redirect traffic to me. So server A receives this acknowledgement and then proceed to apply a redirection rule to redirect incoming traffic from the client to server B by rewriting packet headers, including the IP address and MAC addresses and so on. And finally, everything is ready, and it just unblocks the incoming traffic and tells server B that everything is good to go, it's all yours. Since that the redirection is now ready and the client will be able to acknowledge any packet sent by server B, it now serves the original HTTP GET request from the top with an OK. And the connection is now owned by server B. And subsequent requests from the client will directly end up in server B, and server B will be serving this connection from now on, unless it tries to terminate it. In case server B wants to terminate this offload, it can send the socket back to server A, doing the same process but in reverse. So this is a lot of steps. So in order to check if this is effective, we perform some measurement over this protocol, and this is the breakdown. So we can see that it's pretty okay. So it's in a microsecond regime. So blocking flow takes microseconds, serializing stage code tens of microseconds. But then when we look at installation of a redirection rule, for eBPF it's okay, it's 4 microseconds. But then if we want to use TC, especially with hardware, it becomes hundreds of microseconds, which is quite slow. So this is the detailed measurement result. So we can see that basically they have an orthogonal performance in terms of rule installation and also forwarding rate. So eBPF is really good at doing rule insertion and removal, but because it's in software, the forwarding is not as good. TC with hardware, on the other hand, takes a long time to perform a synchronous rule manipulation, but then it can forward packets at a much higher rate. So why do we not just use eBPF? Because we want to save some CPU cycle, and we also want to use the hardware to perform faster forwarding eventually in case of long-running flows. So why not do both? So we developed we call it hybrid packet redirection scheme on performing this rule insertion. So let's say we have a redirection rule here. So we first synchronously insert this to our eBPF program by updating memory map, right? So once this returns, the rule is already effective, and the eBPF classifier will be capturing the packets and performing redirection. So the offload protocol can proceed and basically done. All right. At the same time, asynchronously, let's say using a thread, we call the Lightning socket and install a hardware TC rule in the background. Right. So if there are any packets coming from the client, it will be redirected by software via our eBPF program. But once the hardware rule is inserted, because it's a low layer, the hardware rule will now take effect. So basically, we are going to benefit from both the fast insertion rate of eBPF and also the faster redirection eventually if the TC hardware rule enters into effect. However, it is not as simple as that because we need to control the ordering of the rule insertion and removal. Let's say we have a very short living flow that takes significantly less time than the hardware rule insertion, which means that the offload might be concluded even before the hardware rule insertion completes. And there is no way to track the removal of this rule because once it's being called, even though NetLink sockets are serialized, we can't do this. So in order to do this, we implement a queue and a worker thread, so basically we use a single thread to loop through a queue that insert rules sequentially, right? Before inserting a rule, we first check in the queue whether there is an offsetting removal request. So if there is a removal request coming in, which means that this stop flow is basically over, we don't need it anymore, and eBPF already did the job. So we simply remove both pairs. And everything seemed to be working until we found a tiny problem. So when I was saying that there are many steps on serializing a connection, this is one of the snapshots. So in this case, we need to check whether the TCP buffer is empty. If it's not empty, meaning that there are some packets, there are some data that are not being received, then we also have to extract it and serialize it. However, if we are using KTLS, we will need the support because apparently KTLS is not returning data with a packet if a socket is in TCP repair mode. So we actually sent a patch, and it's work in progress. It's very small. Anyway, so we evaluate this system using a micro benchmark. Again, we have a similar setup as I described in the beginning for this scenario. We have a 100 gigabit per second link connecting to the outside world. one front-end machine and 4 back-end machines, each of them connected through a 25 gigabit link. Right? So a client comes in, it goes to the front end, opens the socket, and the front end moves this socket to one of the backends to offload the TCP connection. This backend replies the client directly without any involvement from the front end from now on. And when it wants to terminate this offload, it simply moves the socket back to the front end. And at this point, the front end either ends the connection or it can move it to another backend at its wish. So this is the evaluation result. We use the metric throughput and also CPU usage. And we are checking the performance of different offloading frequency. So on the left-hand side, we have the offload frequency of 1, which means that a connection is offloaded to a server, being served, and immediately going back, and then immediately served to another backend again. So this case is similar or equivalent to the round-robin case. And then we have, on the right-hand side, the offload once case, which is the best-case scenario, where a socket stays in a target backend forever. So we can see that in the best-case scenario, we are able to, once the object size becomes slightly larger, we are able to achieve over 80 gigabit per second, despite the fact that each of the machines individually only connect to 25. And at the same time, CPU utilization between backends and frontend are significantly more balanced comparing to the case when we have a simple proxy server. The offload protocol looks quite complicated on the flowchart. So then we are wondering what happens in the real world. So we implemented this in 2 applications. So the first is Nginx, which by default already provides a reverse proxy function where it can forward requests to different backends using policies such as hashing, consistent hashing, or round robin. So we implemented Nginx using the normal way of extending Nginx functionality by implementing it as a module that depends on the HTTP module. It reuses the Nginx event loop to attach sockets, and also reuse the HTTP module pipeline for passing requests and so on. Because we assume a homogeneous backends, so all the backends are the same, we can implement flexible offload and return policies within the module. For example, round robin, handoff once, and so on. And because we use the module interface, we are able to do this with a minimal modification to the Nginx core code. However, we still need to attach some pointers to track connection-oriented data structures. So to use this, we can simply specify the backends in the Nginx, using Nginx directives in the configuration file, and also specify the endpoints. So for example, the front end will listen to socket 80, and this is, and we specify handoff out where it handles incoming connection that will be migrated to other backends. And then we specify a pod that listens to control connections, which handles incoming migrations. So firstly, TCP connections will be coming in on the port from handoff out, like port 80, and it sends the HTTP request. And once the module passed the HTTP request, it serializes the connection, removes it from the Nginx ePO loop, and open a connection to the backend via the handoff import, and then execute the offload protocol. After the backend restores the socket, it runs a relevant Nginx scope to mimic and socket accept and attach any relevant callback functions and data structure. So all future HTTP requests will be handled through the normal HTTP module code path from this point onwards, unless it decides to terminate the offload. So we performed a measurement comparing against normal Nginx front end, normal Nginx proxying using the handoff once. So in this case, XO is handing off a connection to a backend one time, and the connection will stay at the backend forever. And we compare the equivalent in Nginx using consistent hashing, where a particular flow is being forwarded to a specific backend. So we can see in the Nginx case, obviously it's being kept by the link speed at 25, whereas for the XO case, we're able to achieve over 80 gigabit per second. So which means that the outside world link is well utilized. And at the same time, if we look at the CPU usage, in the Nginx proxy case, the front end has consistently higher usage, just like before, comparing to the backend servers. Whereas in the XO case, the usage is much better distributed between the backends. So one of the advantages of using this scheme is that rather than having the front end to decide on load balancing policy and making decisions, the backends themselves who are actually holding the connection can also make this decision on terminating an offload. So in this example, we have 4 backends here, each serving some uniform number of requests. Right. So at the beginning, they are all taking similar CPU loading and also similar sending rate. And at time 30, so in the middle here, backend 1, which is orange, decided to, so the connections connecting to backend 1 at time 30 all terminated, right? So this is an artificial scenario, but it means that backend 1 now becomes empty. So this discrepancy on loading is detected by backend 0, 2, and 3, and they realize that, okay, we are doing too much work. There is someone else who can take the job. So they started terminating some of the connections, going back to the front end, and the front end also looking at the loading and decide to offload these connections to the least loaded server, in which case is backend 1. So after a period of brief fluctuation, we can see that they achieve good balancing again. So Nginx is a level 7 proxy case, and then we take a look at a more specialized case on object store. So in this case, we use Ceph. So Ceph is a low-level object store that is that implements Rados, and it uses consistent hashing on object placement. However, instead of directly using the object store, we typically use it through an abstraction. For example, an S3 object store that implements an object gateway. So a typical gateway works like this. So we have a client, a web client. So it issues a S3 GET request to get an object to the S3 gateway, which is a web server. All right. This server gets the HTTP request, passes the request ID, and performs some hashing. Right? So it uses consistent hashing to check which backend server this object resides. After that, it issues a request to this backend, and this backend fetches data from the storage and returns to the gateway. And finally, the gateway encapsulates this into a reply and then send it back to the client. So a slightly more complication is that in this case, because the backend and the front end are using different protocols and they are communicating using different APIs, which means that other approaches such as splicing and so on cannot be used. And we cannot also use end-to-end encryption between the client and the backend. So we implemented XO as a S3 object gateway, which offloads connections from the front end directly to the object storage daemon that stores the requested objects. And this offload target is driven by the object location rather than policy, like in the Nginx case. So we do this, by doing this, we are able to improve bandwidth usage and data locality because the data is handed back to the client directly from the place where it is stored rather than being relayed through the front end. In this case, we also implemented our hybrid eBPF and TC hardware offloading approach. And this is the result. So we performed a number of GET requests by selecting keys using different distributions. So on the right-hand side, we have the uniform case. And on the left-hand side, we have the very skilled case. So this is the worst case. And the top figure shows the throughput, and the bottom one shows the CPU usage between front ends and different backends. So we can see that XO achieves significantly better throughput and also throughput over the default Rados gateway provided by Ceph. And at larger message sizes, because of faster hardware forwarding, the hybrid approach also achieves better performance than using directly only using eBPF. And we can also see that because the offloading in this case is dictated by object location rather than policy, in the uniform case, the CPU loading for the backends are quite balanced. Whereas on the left-hand side, we can see there is a skewer. So to conclude, we are able to use XO to achieve the best of both worlds between the layer 7 and layer 4 load balancing, where the connection does not permanently reside at any place. And there is also no layer 7 relaying at front end. And we believe that we made the TCP connection offload practical by designing this offload protocol and also eliminating the need for any specialized hardware like a programmable switch. Furthermore, we are able to take advantage of both fast eBPF map upgrade and opportunistically use hardware offloading if provided by the NIC. And we are able to improve two real-world applications, Nginx and Ceph. So if you find this protocol interesting, please reach out. We would like to hear from you. Thank you.
No questions? I have a question. Can you go back to your slide where you're showing the insertion rate? Yeah, that one. Yeah. I think the TC, this is a driver issue.
Yeah.
It's a driver. NVIDIA has a new scheme. I don't know if the NVIDIA people are, something is called like, one goes through hardware, the other goes through software. I think the old scheme used to go through some firmware to update the rules. And the new one goes through hardware directly. I can't remember. I don't know if, do you know?
Joao.
Any idea? The flower rules, no, eh?
So,
firmware and hardware. Okay. You don't know the details. Okay.
so Jamal, I can comment on why the Agilio number is relatively small. Because I made it that way. It cheats a bit. Essentially, it fires off the reconfiguration towards the firmware, but it doesn't wait for it to take place. It just returns immediately.
So it sends a response back saying, yeah, I took care of it, but then it does it in the background.
It's assumed never to fail.
I see. That's a clever trick. I think the Mellanox switch used to do that, I think, in some. Right?
Yeah, I mean, that's a not uncommon model where you, if like Simon said, if the resource is guaranteed, you don't have to worry about failure.
Yeah, but the challenge I think for him is he wants the flow to migrate immediately. And you've just told him, it's done.
Yeah,
and the flow is still going to the wrong place.
Yeah, exactly. I'm not sure that it's actually ready at that point and what implications.
I see.
But I have sort of a related question. So in your picture, you're saying that the flow has migrated now to server B. Somebody is going to have a forwarding rule change, right? Because you're no longer redirecting. So where is that forwarding rule change made?
So the forwarding rule. So basically, we execute the same protocol in reverse, like here in the bottom part. Right?
No, but the upstream switch doesn't know that this destination. So is it an L2 destination?
No, so that we do modify the MAC address.
The MAC address. Okay, so
yes,
you're doing so. That switch is in L2 mode, not L3 mode.
Yeah.
And you're changing the ARP binding basically. You're saying this IP is on the MAC is over there.
Yeah, exactly.
Move the port.
Yeah.
I see. So that's the way to get around this problem. Like as long as the hardware rule has taken effect before the MAC address flip has happened, so you're doing like a gratuitous ARP or something to force the upstream switch. You have to delay that till you know that hardware has taken effect.
Exactly.
It may be salvageable.
Yeah, I think there's no real way to know exactly when it's happened. It shouldn't take that long.
Yeah, that looks like, well, what is that, 2 milliseconds? That.
Yeah.
Yeah. The connected 7 is supposed to be better, I think, but
Yeah,
okay.
yeah.
Did you test with that, Giulio? To Simon's point?
I need to check.
Okay.
We did have an evaluation with Agilio.
Okay, thanks. Oh, there's a question there.
Yeah. So my question is, when we insert this redirecting rule, so it means that at some point of the time, the host that is receiving drops all the packets, and after the retransmission was established, so the next host is like continuing to receiving packets. So it means that so on the sender connection, it looks like we may see a lot of the packets dropped during that time, because like for example, when so if it's more one request sent, because HTTP, for example, supports pipelining and the host can send multiple requests at the same time. So we take a decision, for example, from the first one, and then we decide that we want to offload the connection to another host and drop the rest of the packets. So it seems for that host that, so everything gets dropped, yeah?
Yes, correct.
So, and if it happens in the middle of the connection, you just like ruin the performance of that connection.
Yeah, this is why we implement the hybrid rule insertion scheme to ensure the offloading protocol completes as soon as possible. Yeah.
And another question about inserting rules. So you show the speed of inserting rules. So I wonder why you have such different numbers for eBPF and TC and eBPF XDP mode. So doesn't it just insert the entry into eBPF
because the eBPF is just updating a memory map. Whereas for hardware TC, we need to talk to the network socket, and it has to talk to the driver, and then it has to talk to the NIC, and then it has to reply.
No. I mean BPF TC and BPF XDP. So it's in both cases updating the map, isn't it?
No, for TC, we use the go-through landing socket.
Okay.
No, so in this case, eBPF TC, it means that we use the eBPF classifier and we use TC to perform the action.
But you still transfer entries like what you offload in just inside of the maps. So it should be the same approach, no?
No, it has to go through the driver, right? Because in this case, the eBPF program is simply reading from a map.
Yeah, that gap is too big. It's almost like 10 to 1. No, 10 to 1 for insert, but 2 to 1 on remove.
Yes.
Yeah, that is weird.
Yep.
Okay, if there's no more questions, let's thank our speaker. Thanks.
Thank you.